Okie dokie. Alrighty. Welcome. We're gonna get started with the meeting for today. In case you guys have not had a chance to look at the board quite yet, today we're starting off with an introduction to neural networks. In case you haven't been here before, my name is Jonathan. I'm one of the presidents of Santa Cruz Artificial Intelligence, or SCAI, as we affectionately love to call it. Um, so the theme of this quarter, before we just get into the general discussion of what we're doing today, is going to be a lot of neural network stuff. We want to get you guys into stuff that's a bit more contemporary. A lot of what we did last quarter was very simple statistical predictions. So if you guys remember, we did some linear regression, some logistic regression. We did a Bayesian classifier, k-means clustering, k-nearest neighbors, a lot of stuff that's specifically math-based. And these models are very powerful for what they do, but we are trying to get into things that are a bit more contemporary because they tend to be more powerful than we have right now, or what we've covered so far, rather. So without further ado, let's get started with the winter quarters instruction stuff. Perfect. This should be fun, right? Perfect. All right. So quickly as a preface to the preface, neural models like artificial neural networks, things that you think of when people say neural networks, are an effort at biomimicry. And what I mean by that is there's a lot of similarities between the structure of how a neural network in a computer works to how a neural network in your brain works. In some frameworks more than others, but we'll get into the differences sooner rather than later. So how many of you guys have taken any sort of biology class or have an idea of how a neuron works? Yeah, so generally speaking, would you be able to like give us a overhead view in like a sentence or two of how a neuron does its thing? Do your best, like just like a sentence or two, roughly what a neuron does in terms of like how it acts. Yeah, exactly. So it takes input, does some sort of internal operation, and sends an output to be received elsewhere. And that is the exact same process what we're doing with an artificial neural network. And the similarities are pretty similar. Let's quickly get started with this. So what we're going to be covering objectively is called an artificial neural network. A lot of the time, this is referred to as an ANN or just generally a neural network. So anytime you see someone talking about ChatGPT, transformers, whatever that you see online that's very, very contemporary and modern, they're talking about ANNs, artificial neural networks. And the similarities are very, very simple. So in terms of actual replication to what an artificial and biological neural network could do, they're very, very similar. So biological neural network, a biological neuron, a biological cell, has a few key things as a part of its structure. We have the cell body, we have the axons and the dendrites. And all of these roughly are analogous with a bit of hand waving to what an artificial neural network does. So for an artificial neural network, every neuron, every point in this network that's connected to every other point needs to do a few things. The first thing is that it needs to have an activation function. And all these terms we'll cover in a bit more detail as we get into these slides, but an activation function more or less means when you combine all the inputs, how do you decide whether or not to give an output? And so that's similar to how the cell body works in a natural neuron, like one in your brain. The output is just literally the same as the axon, where the output of the neuron goes as electrical impulse and chemical impulses to the other neurons. And the inputs are the same as the dendrites, where the neuron receives chemical receptors and does some sort of activation within the cell. So these roughly map, and this is the base inspiration for how an artificial neural network works in theory. In practice, it's a little different because of a lot of gross simplifications associated with the activation functions and inputs, but there are some more modern implementations that try to circumvent this, but that's beyond the scope of this specific topic. So let's get into it. An activation function. Simply, an activation function is whether or not there is an output from a neuron. And there's a lot of different ways to do this. So long as the function is differentiable, so you're able to take the derivative of it smoothly on any point, and it's real valued, so there's no imaginary numbers that are going to be spat out of it, you're going to be able to use it as an activation function. So for example, if for whatever reason you wanted to use y equals x squared as your activation function, where every input value is squared, you can use that. It works as a type of activation because it's real valued and differentiable. And so a few common ones we put on screen here. We have the sigmoid function, which I think we've talked about before. More or less, it's just a nice way to cleanly differentiate from 0 to 1. It's very, very similar to tan h, but from -1 to 1. And both of those can be used for clean statistical prediction. So what ends up happening with both of these functions is values that are much closer to zero get amplified towards 0 and 1. So if you take the sigmoid of, let's say 1, that's going to be 1 over 1 plus e to the first, which is going to be roughly 1/4. And for a value of 0, you're going to be predicting just 1/2, because anything to the 0th power is 1. So with 50% probability, you're going to be at 0. And it's the same thing, just continue in both directions. Similar for tan h. If you guys want to look up the hyperbolic tangent function, that's what that is. ReLU is a very, very simple one, more or less. The name ReLU just means rectified linear unit. So it's just a linear function. This is the line y equals x, but below the value 0, we're just always doing 0. That's it. It's very, very useful. We're going to use it a lot coming over this next quarter and going forward as well. Leaky ReLU is the exact same thing, except instead of 0, you're just going to be multiplying the input by like a fractional value. This is really good for minimizing underfitting, because you're not going to be just completely chopping off values that you might otherwise want to use. Max out is pretty uncommonly used, and LU is another modification on ReLU. It's just it's a different transformation. So these are just a few examples. I know we're going a little bit quickly, but all of these, with the exception of max out most of the time, you'll see used in artificial neural networks. Any questions so far about like what specifically this might mean, how we might use this, or where it might come into play? Yeah. What case is it significant? What do you mean by significant, I guess, is the first question. Perfect. So in the case of sigmoid, more or less is, we'll actually show this on the next slide, so we'll just go into that, and we can talk about that. So this more or less is what every artificial neuron looks like. So we take the inputs from every other neuron that it's connected to, so in a fully connected way, where every prior layer connects to the next one, or every neuron in the prior layer connects to the next one. We're taking that input, multiplying it by some weight, which is written here as omega. These are often stored in a vector. And sum together, plus some sort of bias term, which is also learned. So in a neural network, all of the values that are being learned here are the bias and weights. So for every neuron, you're learning all of the weights that are associated with the prior layer and the bias that's associated with that activation. So the activation specifically just tells you, okay, based off of this sum and passed into this activation function, let's say we're using ReLU or something. If it's less than 0, if we get a negative value, we don't want anything. If it's greater than 0, we want the sum. For something like sigmoid, we're going to be taking that sum and passing it into the function, and that's our output. So it's significant in that we're able to specifically dictate what goes on and what gets spit out. And for something like, for image processing, a lot of the time you're going to want to use things like sigmoid because you're able to get a wide range of values. And for something like language manipulation, you're going to want to trim a lot of lower probabilities. Something like ReLU a lot of the time fits better. But there's exceptions to these rules, and we'll get into specifics as we go along. But yeah, this is generally the structure of an artificial neuron. So what we're seeing here is input to output, and this happens in every single cell, every single neuron. And you can have tens of thousands or millions of these to get something that's sufficiently complicated and do something that's sufficiently powerful. And the really, really cool thing is that it can predict things that you might not have enough data to predict a clean function for. So it's very, very useful for regression, classification, and prediction. It's very, very powerful. And that's why we're very happy to be talking about it. And so if you want a mathematical representation, that's in the bottom left here. So what we're doing is we're taking the weight vector times the input vector, or excuse me, doing the dot product of the weight and the input vector, which you guys might have seen in your linear algebra courses, and adding the bias term. This can also be represented as just the sum for every weight, weight I and xi plus a bias term. And that gives us our sigma here, which is our activation, or our sum. Or which, sorry, this is our sum, which goes into the activation to the output. Everyone clear so far? Thumbs up, some sideways, some down. Great. All right, let's keep going. Kevin, do you mind for some things? Thanks, bud. Cool, cool, cool. Okay. Now we're going to get into something that's a little more complicated, but we're really not going to get into the math because it's a huge headache. Gradient descent. This is what makes artificial neural networks possible. Like the fundamental learning that occurs is because you're able to use the activation function and the weights and do back propagation. Gradient descent is effectively just taking the chain rule of partial derivatives. So starting at the output, you're going to be working backward instead of forward through the network and updating the weights based off of the errors. So what we're doing basically is if you look at this representation, this is often called a loss landscape. So just like the 3D or multi-dimensional representation of what the loss function looks like. So how we're defining what we want to approach, what we want to optimize. So what we're doing is for every step in our function, we're trying to go to the lowest amount of loss. And the way we do that is by working backwards through the function. So we look at our output. If that matches, then we don't update the loss. Then we take a step back in the network. If it doesn't match, we update. We try and get the values really, really specific and really, really refined to the one task. And without getting too much into the math, because it's not particularly interesting and out of the scope of what we're doing here, this is the whole that makes it work. You do not have neural networks without gradient descent. And it's a very, very powerful tool, as you'll come to see when we actually implement this stuff. Not necessarily this week, because what we're doing is not a great function, but this is very, very important as a concept. And if you're interested, I suggest you look into it yourself. The math isn't the most complicated, it's just a little out of scope for what we're doing. And if you know how to do partial derivatives and the chain rule of partial derivatives, you'll be fine. It just takes a bit of time to get a real comprehensive understanding. Okay, perfect. So before we go on, is everyone feeling decently confident? Like you could, I don't know, regurgitate 3 words about what I've said this entire time to me. It doesn't really make a huge difference, just that you aren't completely lost, because we're going to be going into something a little less cerebral to more application focused at this point. Thumbs up? Sweet, okay. So that's more or less the basics for what we're doing in terms of a theoretical standpoint for now. And we're going to go on to just the application that we're going to look at today. So for something like, let's say, classifying what a cat versus a dog is in an image. Say you want to make a predictor for that. What would you do? Like a lot of you have been here for the past quarter. What sort of functions would you want to do with this? If you know anything about neural networks, feel free to say it. Well, take a couple minutes, discuss based off of what we covered here, what you already know, and try and come up with an approach that would be able to classify the difference between a cat and a dog based off of an image. Go ahead, talk amongst yourselves. This is like another slides. Nice. Okie dokie. Does everyone feel ready to discuss or present some ideas, or do we need another minute? All good? Sweet. All right. Does anyone have any ideas? How would you tell what the difference between a cat and a dog is? Yeah. Yeah, that's a great pick. As a quick question for you, how would you tell the difference between, oh, I don't know, what's a dog with pointy ears? Like a Chihuahua versus a house cat. That's another good one. Yeah. Over there. Snout. Nice. Anyone else? Yeah. Claws. Yeah, like whether or not they have claws. That's a good one too. Uh-huh. Yeah, in the back. Hmm. Mm. So you're suggesting something like a kind of rule-based system. So everyone has a theoretical understanding of what a cat and a dog is and can like fundamentally collaborate to understand that? Ah, I see, I see. That makes a lot of sense. Yeah, yeah, yeah. Anyone else? Yeah, kind of the teeth. That's a good one too. So a lot of focus on physical characteristics, which is good. We're analyzing images. This is something that's very, very important for what we're trying to do here. Does anyone have any inkling of how we might want to do this with a computer? Like in any approach, like a computer doesn't have a good understanding of what is an ear or what is a tooth, really. It has understandings of how pixels relate to each other after learning for hundreds of generations, but how would a computer want to do this? Yeah, that's good. That is good. Yes. How would you take the tooth then and put it on the main image? How would you compose it to be able to learn from the tooth to the cat? Yeah. Right. Yeah. You guys are getting at something. Yeah. 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 No, that's definitely right. Focusing on specific features for what we're looking for. Absolutely. So, as a general question for everyone first, could we not also do the same thing, but on the whole image of the dog and the cat rather than picking out specific features and letting instead the model pick out what we're looking for? Yeah, and that's generally what we're trying to get at here. The way that we do this is a long process of learning where we just give it labeled data, specifically for neural models. It differs for other things that are self-guided and more interesting and complicated things we could go at for this. But generally speaking, we want to give it labeled data so we can learn a labeled output. Because we're not looking to cluster, we're looking to classify. Everyone good on this? Perfect. All right, next slide. So this gets us to the algorithm of the day, which is lovingly holds a space in my heart. It's called the perceptron. The perceptron has some really, really cool history. Kevin, you're gonna need to idle through this one. Perfect. So this was first introduced in 1957 by Frank Rosenblatt. I love this. It's so dumb. Keep going. This is the paper in case you guys want to read it. We're gonna put up the slides. It's very, very readable and perceptible. It's like it basically just uses a linear algebra. If you guys more or less understood what we were doing with the single artificial neuron, read this paper. It's a hoot. It's like 20 pages long. I read it myself. Keep going. This is what it looks like. This thing here, sorry, this is the perceptron as was originally built. It's really, really cool. If you go to the next one, again, perfect. It uses 400 photoreceptors. So basically just like a bunch of light receiving diodes and manually takes the cables out and processes the signals and does gradient descent on the output of those layers and tunes the weights, next one, with potentiometers. So just basically the strength of the signal is encoded to the weight. So it's really, really cool. It's a physical neural network. Like, excuse like doing things in software in like in a little program or anything. This is like a physical thing that receives like images based off of light and can spit out an output. And it's really funny because the Navy called this the embryo of an electronic computer that they expect will be able to walk, talk, write, reproduce, and be conscious of its existence. And the best thing about it is that it's used for binary classification. So it's really fun. I love this program a lot. It's super, super foundational, and we'll get into why in the next week. But more or less, the perceptron, and by extension, putting a lot of them together, is the foundation for neural computing. Because you're able to take the output of one perceptron and feed it into another one. So making it multi-layered. And if you guys have read any papers or just heard any conversation about machine learning or artificial intelligence in general, this is often referred to as an MLP or a multi-layered perceptron. If you're talking about something like a feed-forward neural network, which we'll be talking about at length in the next couple of weeks. I know I'm kind of going quick about this, but I really, really love this algorithm. I just want to get you guys super excited about it. And this is how it does its activation, as in the original paper. So what it does, if you guys remember what we did before, and we looked at the activation functions, it just makes a decision, more or less, if the weights and the dot product of the input values plus a bias term is greater than 0, then it predicts 1. Otherwise, it's 0. That is it. It's just a linear step function. If you go to the next slide, this is all it does. So anytime that we're talking something that is less than 0, it predicts 0. Anytime that it is greater than 0, it is 1. And this is the decision boundary. This will always be undecidable. So for our purposes, we're doing something a bit different when we're implementing this, but it is super, super rudimentary and super, super simple. And this is the foundation of all neural computing. Like, we're starting with this because it's a very, very good look into how this stuff kind of works. And I'm super, super excited for us to have an opportunity to go there. Is everyone feeling pretty confident about the perceptron in theory, not in practice? So perfect. Okay, very good. So with that, I think we'll do a quick little summary of what we've covered so far, just in case anyone has any questions that they haven't brought up yet. Okay, so let's start here. For the activation function, the main thing that's important here is that it's just a way to take input that's been processed, multiplied by the weights that are learned, and process it as output. So this can take form as any function that you want, so long as you can differentiate it. So take the derivative of it, and it spits out real numbers. So not imaginary numbers, basically. Any complex numbers, imaginary numbers, you can't use. You can't do anything with it particularly. So we're concerned with negatives and positive numbers. Anything on the real number line. Gradient descent, after we look at this is just the, this is the individual neuron. This is basically the perceptron as we're considering it for today. And gradient descent is just the process of learning on an artificial neural network. We're going backwards across. This is often called back propagation because we're working against the flow of the network. So instead of going from input to output, we're going output to input and updating the weights. All right, this is the general foundation that we need. Sure, yeah. And generally speaking, if we go back a slide, oh, there we go. If we go back a slide, the input and output for a single neuron, in more or less simple terms, the output is the prediction and the input is anything that is based on that prediction. So if we're doing something like image prediction, an input can be the color value of a pixel. If we're doing like language prediction or something, what we can do is tokenize or take a sentence and turn it into integers and pass that in as well. So anything that you can act on as literally just data to make a prediction is considered input, and what we're spitting out is our output. And it becomes really interesting when you string them together. So taking outputs adds inputs. But that is more or less the foundation of what we're going to be covering today. So quickly, before we get into the practical portion of today's meetings, anyone have any questions? Yeah. Yeah. How do you mean? Yeah. So okay. This is a very good point that we haven't had a chance to touch on. Gradient descent only occurs as a learning step. So what you do in every iteration of every step of learning in a neural network is you make predictions, and then you see if you're wrong. And if you're wrong, you make updates. If you're right, you don't do anything. And so that process more or less looks like going backwards. So go back to the previous slide. Perfect. So instead of what we're doing, we're starting at the output. We know we got the output wrong. Okay, so let's go back. The activation function is fine. You can't edit this. It's just literally a modification of the values here. We're going to go to the sum. We can change the bias term. The bias term is just a value that we always add. It's basically its own weight times 1. It just is its own learnable parameter. So you can increase it, decrease it. It's like, it's real value. So any fractional whole number value can be huge, tiny, it doesn't matter. It learns what the bias is. And if we take another step back, we can also learn what the weights are. And basically the process of doing this is just doing partial derivatives with respect to each of these values. So for each weight, we're going to do the partial derivative of omega m, the partial derivative of the output with respect to omega m or something, right? So we're just looking at the one weight and learning the difference from what we got to where we're at. Again, it's a lot easier to understand reading it rather than hearing me describe it without the whole thing, but it's not the most complicated thing in the world. Granted, you know partial derivatives and the chain. And this step always happens during learning. So you make predictions, see if you're wrong, update the weights. And that's the learning loop the entire time you're learning. Yeah. Yeah, sure. So basically, the input values are the input values, but they're not particularly useful as just input value. So what you want to do is be able to modify them and learn what each of them do in every step. So if, for example, we didn't have the input weights, we're just going to be taking these into the sum and into an activation function. There isn't any learning. So in order to make some sort of prediction, we need to be able to modify what we're seeing and make it more or less important. So if, for example, we're using the cat versus dog prediction, if the model learns where the ear is and is able to distinguish based off of some edge, that's going to be more important for it compared to something like a part of the body which isn't very specific or useful. So the weight specifically just represents what is the input and why is it more important than everything else. It's just a scale. Good question. I didn't get a touch on that. Anyone else? Oh, one more question. Uh-huh. Okay. Actually, that's out of the scope. We don't talk about loss functions for this, but more or less as a general overview, a loss function is just a way to evaluate the fitness of a weight. So if it is close or if it is far away. So for something like, I don't know, let's say, what would be a good loss function? It's really, really easy. Like L1. Yeah, L1's really easy. So what we do basically, hold the mic.
Uh, yeah, so gradient descent is, wait, Cohen, can you go back to the, so this graph is a graph of the loss. And gradient descent is the process of trying to find the lowest point of loss. So down here, this is where we're trying to get to. We're trying to get here where the loss is the smallest because we want our model to be accurate. We want it not to be lost. Loss is how poor of a job it's doing. So we want to minimize that. And gradient descent goes, hey, the loss is this much. Let's try and figure out how to get down here. And so partial derivative, who here knows what a partial derivative is and has worked with them? Okay, some of you. Who here knows what a derivative is? Okay, awesome. So a derivative, you take a function and you get like what direction that function's going in, correct? Does that make sense as kind of one of the definitions of a derivative? Cool. Partial derivative is doing that in multiple dimensions. So you take this function, you go here, you say, hey, the partial derivative, what direction is it going in? And then you follow that all the way down to the zero. That is gradient descent. You're going and looking at the loss and trying to make it the smallest by using the derivative in multiple dimensions. And then you're going back and updating the equation to try and make that loss go down to a minimum by going along that function. Does that make sense? Cool. Not quite. The loss function is where you are currently. And then the gradient descent, you try and figure out what this shape is, and you try and get down to the bottom of it. The loss is only where you are. This is a graph of loss. The y-axis in this graph is the loss. So if you're at a height of, let's say, 2.0 at this graph, that means the loss is the value that we just went over right here is 2.0. That's what this graph is. It's a graph of loss, and then here are going to be the like parameters.
Without getting too into the weeds, loss specifically for our case and most cases is looking at what we have and what we want to have and making a calculation that way. Gradient descent is going against the direction of the gradient. So for derivatives, a lot of the time that represents the like graph. So if I do like x squared here or something, just like 1/2 of it, the derivative is going to be going this way because it's a point tangent to the graph. So gradient descent is going in the opposite direction. So we're going to do the negative derivative and go to the lowest point. And you do that with the loss function, basically. So you evaluate that, you calculate the change in the loss, and you go against that curve. So that's why you descend instead of ascend. This was very, very in the weeds for our purposes, I feel. But any additional questions about this specifically, or are we feeling all right? Yes? Cool beans. Okay. And before we move on again to the practical portion, are there any other questions specifically associated with this type of prediction, with et cetera, et cetera? Anything associated with what we've covered today about the basics of artificial neural networks?
Generally overall idea of what is. That's all we're looking for.
Okay, perfect. If everyone's feeling up to date, here's what we are going to do now. We are going to go right to the end of the slide deck, and we're going to do the practical portion. So, everyone wants to stand. What do you feel about that? I will leave this for everyone to get up, and then I'm going to end the recording for the funny people on Zoom Land. Bye, guys.